Hello, my name is Junha Kim, and today I will present about leg robot state estimation with dynamic contact event information. State estimation of leg robots takes an important role in leg robot control. For example, if you want to make the robot to go on a high obstacle, you need an environment map and also need to calculate a tracking error to compensate the robot to follow a desired trajectory. Both tasks need an accurate state of the robot, which makes state estimation as one of the key elements. Many researches with visual inertial navigation system showed a great result in estimating the robot state accurately. However, when cameras fall into featureless scenes, like the videos shown below, it can have a trouble. In this reason, proprioceptive only state estimation is still important and widely used state estimation method. Leg robot state estimation with only proprioceptive sensors usually utilizes inertial measurement unit and encoder measurements. Especially for encoder measurements, joint kinematics models are used with an assumption of fixed contact of the foot. However, in many scenarios, foot contact is not always fixed and stable, mainly due to slippage, unstable ground, and contact estimation error. We show you the videos for example. You can find out that while robot is making contact with the environment, it suffers slippage or unstable ground. Our main goal is to design a proprioceptive sensor-only leg robot state estimation algorithm while taking account of these dynamic contact events. Now let's start with our definition of the problem. The state estimation problem can be defined as a maximum a posteriori problem, which solves for getting the states that maximizes the multiplication of measurement probabilities and prior probabilities. This can be further changed to a nonlinear least squares problem by assuming that all probabilities are multivariative Gaussian distribution. To solve the nonlinear least squares problem, many algorithms can be used, but in this paper, Gauss-Newton method is used, which utilizes gradient of the cost function and the Gauss-Newton Hessian approximation of the cost function. Gauss-Newton method uses only the first-order derivative information of the cost function to find a good search direction. The solution is obtained by iteratively updating the variables with this search direction until convergence. By defining the residuals and covariance matrices of the Gaussian distribution and the Jacobians of the residuals from the measurement models, the MEP problem can finally be solved. However, since our states include rotation matrix, which is a 3D special orthogonal group, over-parameterization problem can occur. This is carefully handled by the reparameterization through Lie group theories, which is well explained in the reference articles. To briefly summarize, original optimization of manifold is projected to the tangential space, which is further mapped to the vector space. The optimization problem is solved in the vector space, and the solution is retracted to the original manifold space. In our paper, we derived our analytical Jacobians of the residuals with respect to the change optimization variable delta x utilizing the Lie group theories. Now with the change optimization problem, we can properly solve the nonlinear least squares problem with Gauss-Newton method. Although the estimation algorithm can be modeled as previously spoken MEP problem, as iteration goes by, new states and measurements should be continuously added, which means that iteration becomes more and more expensive. In this reason, we adopt the fixed leg smoother method, which marginalizes the oldest state when a state window becomes a certain size. The procedure can be explained graphically. As you can see, the new states and measurements are concatenated to form a bigger and bigger size of optimization problem until maximum window size is met. When the window size exceeds the maximum window size, the oldest state is marginalized by sure complement method and becomes a new marginalized prior, which makes the problem a fixed size. Since we talked about the overall procedure of the estimation algorithm, let's go a little bit more deeper to the details. For the residuals and covariances, we have a total of 4 kinds of models: prior, IMU, kinematics, and biases, which can be represented as a vector graph model as below. Between these models, the kinematics measurement models assume that the foot in contact does not move. As we talked before, this assumption is generally not true due to the dynamic contact event situations. To cope with this problem, we introduce a method named slip rejection. This is done by first estimating the foot velocity as the equation below, and if the norm of the velocity is over a certain threshold, rejecting the kinematics measurement. You can see from this graph that by using the estimated foot velocity norm, we can know when the foot is slipping, and this information is used to reject the kinematics measurements in the estimation algorithm as talked before. We can find the effect of the slip rejection method from this graph, where the red region means estimated slip states. As red region becomes darker, it means that more foot is slipping. The estimated velocity with slip rejection method has less error when many feet is slipping, like black circled region. We verify the performance of the algorithm in 4 scenarios: rubber surface, slippery surface, unstable terrain, and circular. The invariant extended comma filter algorithm was used for comparison. The rubber surface scenario's environment is constructed by attaching a high-friction rubber tile on the floor. The slippery scenario's environment is constructed by spreading boric acid powder on an acrylic plate. The unstable terrain scenario's environment is constructed by installing rock pebbles on the wooden structure. Finally, the circular scenario's environment is constructed with a combination of rubber and slippery surface. First environment is the rubber surface environment. In this scenario, the robot walks back and forth for approximately 103 seconds, with approximately 56 meters as the total length of the trajectory. As you can see, blue robot, which is the estimated result of our proposed algorithm, had less drift than the red robot, which is the result of IEKF. The second environment is the slippery surface environment. In this scenario, the robot walks back and forth for approximately 110 seconds, and with approximately 54 meters as the total length of the trajectory, while making slippage on rapid velocity changes. The error of the estimation of IEKF gets larger when slip occurs, while the proposed algorithm reduces this effect. You can see the proposed algorithm could reduce the final position drift than the IEKF algorithm. The third environment is the unstable terrain environment. In this scenario, the robot walks back and forth for approximately 140 seconds, with approximately 34 meters as the total length of the trajectory, while the contacting rock continuously moves. As you can see, the proposed algorithm could reduce the final position drift than the IEKF algorithm. Finally, the fourth environment is the circular environment. In this scenario, robot walks a circular trajectory for approximately 80 seconds, with approximately 37 meters as the total length of the trajectory. As you can see, the proposed algorithm could reduce the final position drift than the IEKF algorithm. The average absolute trajectory error and 10 seconds relative errors means and covariances are summarized in the right side table, and the proposed algorithm had better results in most of the scenarios. We could find out that major improvement came from the slip rejection method, However, the estimation result of proposed framework with slip rejection method still had better result than IEKF with slip rejection method. Okay, now, this is our conclusion and future work. The state estimation algorithm for leg robot as a fixed leg smoother with an appropriate derivation of required equations using manifold structure of SO3 is proposed. Slip rejection method is proposed to deal with dynamic contact event. And the proposed estimation algorithm is verified on various environments with respect to IEKF algorithm. And the future work covers invariant smoothing framework and real-time implementation by optimized coding. This is the end of my presentation, and thank you for listening.